I want to finish the logistic growth model, actually showing you some full problems we're going through and continue to have some of the discussions that I did in the intro video. So here's where we left off. We have these formulas to use to do a logistic growth model. And as I said on the last video, I will not make you memorize these. So here's a disease problem, super exciting topic to talk about here. We are spreading a disease. We're not going to talk about people right now just because I don't want to be depressed. So we're going to spread Asian beetles. And yes, I realize Asian is spelled wrong. This was copied from a student's notes that are spreading through a grove of trees. And we have a grove of 60 trees and we're spreading it by the equation dp dt, and then that is listed for you. Notice my 60, which is my carrying capacity, is the denominator here. This value right here, the 0.71, that's going to be your K value. Sometimes they will give you a K value. Sometimes you have to go through the work of finding it yourself. But this one's kind of nice because they do give you a K value of 0.71. So some questions that I could ask, when would the spread of the beetles through the trees be at its highest, at its peak? And that's going to be at half of the carrying capacity. So once these beetles have spread to 30 out of the 60 trees, you are at peak spreading. At that point, we will continue to spread the beetles through the trees, but it will slow down. So then they give you some extra information. So on day one, or day zero, technically, on the start, we only have one tree infected. We want to come up with a logistic growth model of the infected trees and then use that to predict when half of the trees will be infected. So we'll know when we get to that half the carrying capacity. So we have our formulas that we're going to use. We need to find the A value first. So your A value is going to be your carrying capacity minus your initial. So my carrying capacity is 60. My initial is just one tree is infected over 60. So I'll end up with 59, or excuse me, not over 60, over your initial population, which is 1. So I'm going to end up with 59 over 1, or in other words, 59. So again, taking my carrying capacity minus my initial population divided by initial population will give me an A constant. So then we're going to put that into our P equation. So our carrying capacity again is 60, so that's your L. You're going to have 1 plus 59 e to the negative, we have our K value, 0.71 t. And we're going to use this to figure out when my population will get to the point that 30 of the trees are infected. So we're going to set that equal to 30 and solve for t. Now I'm going to do a lot of the work kind of on my calculator behind the scenes, but I will talk to you about it a little bit. You're going to want to cross multiply. So you're going to multiply the entire denominator by 30. Then you're going to, so I'll write that down. So 30 times 1 plus 59 e to the negative 0.71 t equals 60. Then you're going to divide both sides by 30. Then you're going to subtract 1. Then you're going to divide by 59. Then you're going to take the natural log of both sides to get the e. And again, all these steps kind of can happen on your own without doing a lot of calculator work. And eventually, you're going to solve for t after all of that and get t to be about 5.743. These are days. So what that means is it's going to take about 6 days for half of my trees to be infected. So at that point, that's when the rate of infection is the fastest. From after day 6, then the rate starts to slow down. So that is how you go through and do a full question. Truly, they don't ask you to do a lot of full questions. Usually they ask you more conceptual based questions about the carrying capacity, but that's how you would do a full disease question. So here's how we do a full rumor question. So we have a school of about 1,400 people. So I tried to model this example around Twinsburg High School. Initially, 20 people have heard the rumor. 100 people have heard the rumor 2 hours later. The question is, how many people have heard it after 6 hours have gone by? So we want to start with our A equation. So our A is our carrying capacity, which in this case is the entire population. Once we get to 1,400, everybody will have heard the rumor, minus the 20 people that heard it initially, divided by 20. So again, you can use your calculator. You're going to take 1,400 minus 20, get your answer, and then divide by 20. You end up getting A to be 69. It will be a constant. It will be a positive constant. So my equation is P equals L. So L is my carrying capacity of 1,400 divided by 1 plus my A value is 69, e to the negative K times T. So now we're going to put in our initial information as far as like the pair of information that they give you, just like we do with regular exponential growth. We have to find a way to get K if we aren't given it directly. So I know that after 2 hours have gone by, 100 people have known the rumor. So 100 equals 1400 over 1 plus 69 e to the negative 2k. So we're putting 2 in for your time and 100 in for your population. Again, at this point, it's a whole lot of behind the scenes algebra. You're going to cross multiply, you're going to divide, you're going to subtract, you're going to divide, you're going to take the natural log. It takes a while to get there, but it's all an algebraic solving of k. I guess the first thing is to keep in mind, just write it as a proportion and cross multiply, and that should get you going. Your k value, it is positive. It is 0.835. And that's after we've done all the algebra. Now we're going to take that value and we want to figure out how many people have heard the rumor after 6 hours. And again, this k value, I don't want to round it, so I'm sure it's not exactly 0.835, but you want to keep it in your calculator. So now we're going to take our 1400 over 1 plus 69 e to the negative, and then I'm going to have my k value that I just found, and then I'm going to have 6 because that's my time that I'm working with. I'm going to take the k value times 6. I'm going to take it times a negative. I'm going to take e to that power times 69 plus 1. Whatever I answer again, that's going to be my entire denominator. I'm going to take 1400 divided by that denominator. And what I find out is after only 6 hours, 958 people have heard the rumor. I can't have part of a person, so you're always going to round to the nearest whole number when you're dealing with something that can't be partitioned. Couple just basic ideas, kind of things to talk about that were beyond using this formula and doing all the arithmetic. Since the school had 1,400 people, once we get to 700 people, that's half the carrying capacity, the population will be growing at a rate at the fastest rate because it's half of the carrying capacity. We will see that, so the 6 hour mark, that is, we're over half the population. So we are still increasing at that point, but we are increasing at a decreasing rate. We would say the graph is concave down after it gets to 700 people because it is increasing at a decreasing rate. So that's how you do the logistic growth. Again, they don't ask you to do a lot of full length problems like I just showed you. They do a lot of quick problems asking you about carrying capacity, asking if it is logistic growth, and asking about the concavity. But this is how you go through and do a full problem. And these formulas right here will always be given to you. You do not need to memorize it. And hopefully this helps understand logistic growth.